Today, we're going to be talking about the energy transfer that happens in chemical reactions. We've talked about chemical reactions quite a bit so far. Whenever we have a chemical reaction, we have the reactants, and there's bond breaking that happens, and new bonds form. And so we get new products that happen. That's sort of a definition of a chemical reaction. And anytime we have a chemical reaction, there's always a transfer of energy. And so today's lesson is really going to focus on determining if a reaction releases energy or absorbs energy. So we'll be defining chemical reactions as being either endothermic or exothermic. So we'll go through a couple of slides very briefly, and then we'll get into a few practice problems, and I'll show you exactly how we go through this process to determine if a reaction is endothermic or exothermic. Now, in any reaction, there's always two steps. Actually, I guess I shouldn't say always, but in general, there's two steps. The first step is bond breaking. So if we start with some reactants, atoms that are already bonded together in some way, in order for a chemical reaction to take place, we first have to break those bonds apart. We have to pull atoms apart that are already bonded together. That process is energy absorbing. It takes energy to pull atoms apart. And that makes sense, right? Because if atoms want to be bonded together, either ionically or covalently, they want to be together. They're attracted to each other. So in order to pull them apart, energy has to be put into pulling them apart from each other. The second part of this process is bond forming. So when we first pull atoms apart and then they interact with other atoms, the forming of new bonds is actually an energy releasing process. So there's always two steps. First, in a chemical reaction, bonds have to be broken, and then new bonds have to be formed. And this is kind of an example. It doesn't always happen in this order, but you can see in this chemical reaction, we have some new bonds forming and some bonds breaking. And that because both of those processes are energy absorbing and releasing, breaking bonds and forming bonds, that leads us into this concept of having endothermic and exothermic reactions. So an exothermic reaction is where more energy is absorbed. I'm sorry, I'm talking about endothermic here. And in endothermic reaction, more energy is absorbed overall than is released. And remember, I just said that bond breaking is an energy absorbing process and bond forming is an energy releasing process. So, in an endothermic reaction, more energy goes into pulling the current reactants apart, the bonds apart, breaking bonds, than is actually formed when the new bonds are formed, released when the new bonds are formed. Oftentimes, this is an essential thing that whenever this kind of reaction takes place, where is that energy coming from? Where is the energy absorbed from? And it's usually absorbed from the surrounding environment. So let's just say we have a beaker of water and we run a reaction in that beaker of water. And if it's an endothermic reaction, the energy is going to be absorbed from the surrounding water molecules. So you can think of the kinetic energy of that water as a certain temperature, and as the reaction happens, it actually takes heat energy away from the water molecules that it's in and puts it into the reaction. That's going to cool down that water. It's going to feel colder. So in an endothermic reaction, the surroundings, whatever the reaction is taking place in, the surroundings are going to cool down because that's the energy is going into the reaction and away from the environment. So a few examples: photosynthesis is an endothermic reaction, cold packs, and a lot of decomposition reactions. Okay. The opposite type of reaction is an exothermic reaction. Exo means out, thermic means heat. So in this kind of reaction, more energy is released than is absorbed. So in this case, remember there's two steps: bond breaking and bond forming. Bond breaking is an endothermic or energy absorbing process, and bond releasing is an exothermic or energy releasing process. So, in an exothermic reaction, more energy is released than is absorbed. Because energy is released, typically that is in the form of thermal energy. And so that's going to warm up the surrounding environment. Again, if we take our beaker of water and we have a reaction that's happening that's exothermic, the water is going to get warmer. Okay, so we have a lot of examples of these. If you've ever used a hand warmer when you go skiing, you break that package open, that nice orange package, and you wiggle it in your hands, and a few minutes later it starts to warm up. That's an exothermic reaction between iron and oxygen. All combustion reactions are exothermic. When we take anything and we burn it, we're going to give off heat and light. Those are energy releases, and those are always exothermic reactions. And there's a bunch of other examples on here as well. So, um, in general, quick summary, endothermic reactions that there's more energy breaking bonds than there is forming. And in exothermic, there's more energy in the forming of bonds than the breaking of bonds. So those are some key concepts with all of this. The rest of these slides you don't really need to know. Actually, this last one is what we're going to get into next. How do we actually determine if I have a chemical reaction? How do I know if it's endothermic or exothermic? And if you're thinking, well, bonds are involved here, so there must be something that has to do with bonds. That's right. We have to know about the bonds. So our first step is going to be to balance the chemical reaction, which we recently learned how to do. Then we will determine the Lewis structures for all of the reactants and products. The reason we do that is that will tell us what kinds of bonds are being broken and which kinds of bonds are being formed. And then we'll use the bond energies. Every type of bond has a specific energy associated with it. So we'll look at our Lewis structures, look at the bonds in the Lewis structures, and add up the total of energy in the products and reactants, and then we'll determine which there is more of. So that's our next step. Now you're going to need a few resources in order to do this. The first thing that you're going to need is a periodic table. Okay, you can get that pretty much anywhere. That's going to help you draw your Lewis structures. The second thing you're going to need is a table of bond energies. So I'm showing you this right here. This will be provided for you in class. It's not something that you'll ever have to memorize. And if you are working on some work at home and you don't have this for some reason, you can always Google table of bond energies. You're going to find something similar to this. The values may be slightly different. That's because these are all experimentally determined, and so we can get a little bit of variation in the values, and that's no big deal. So if there's a little bit of difference in the energies, you don't need to worry too much about that. And then we're going to be doing a few example problems. So you might recognize these if you got these in class. We're going to be doing a few example problems together to help you understand how to go through this process. Okay. All right. I do want to give you a little disclaimer that this is a very basic process that we're going through. Although there's a lot of technique involved, a lot of skills involved, there is very much more going on than we're talking about. We're simplifying this process of bond breaking and bond forming. There's a lot more to it. And so in a higher level class, you might actually learn quite a bit more about this than what I'm showing you now. And that's fine. We've always got to start somewhere. So let's go ahead. We've got our periodic table. We have our table of bond energies. Let's go ahead and start with our first reaction. The first reaction that we're going to work with is actually the combination of nitrogen gas, which is N2, plus hydrogen gas, which is H2, and that's going to form a very common molecule called ammonia, NH3. Actually, there's a lot of history behind this process, and a very famous, I believe it was a German, came up with a process to make this reaction happen in an efficient way. It's called the Haber process, and it actually led to kind of revolutionized a lot of different things like warfare and agriculture, because these nitrogen compounds are pretty important for making gunpowder for war and also making fertilizers for agriculture. Okay, side note though. Um, Remember, the first thing we want to do in this reaction is we want to go ahead and balance this reaction. So let's go ahead and use that process that I taught you. The only two types of atoms we have in this reaction here are nitrogen and hydrogen atoms. And remember, the purpose of balancing a chemical equation is to make sure we have the same amount of atoms on both sides. We're following the law of conservation of mass, so we have to start and end with the exact same amount of atoms overall. So we're going to assume, I don't normally do the ones here, but let's just assume we have one of each to start. So if we total up, we have 2 nitrogen atoms, because 2 times 1 is 2. Sorry, 1 times 2 is 2. And on the reactant side, we have 2 hydrogen atoms as well. And if we look over here at ammonia, we have 1 times 1 nitrogen, which is 1, and 1 times 3 hydrogen, which is 3. So this is not balanced because we don't have the same amount of atoms on both sides. Let's go ahead and balance it. I'll start by adding a 2 over here, and that's going to give me 2 nitrogens, and 2 times 3 hydrogens, which is 6. Okay. And then I need to come over here, and nitrogen is balanced, which is great. Hydrogen is not, so I need to change this coefficient here into balancing. And if I put a 3 there, excuse me, if I put a 3 there, that's going to give me 6 hydrogens. Okay. All right. So now this is balanced. We have coefficients of 1, 3, and 2. All right. Let me clean this up a little bit. So let's put a 1 there. Let's put a 3 here, and we'll put a 2 here. Okay, just to clean it up. Now we have our balanced reaction. That's always the first step. Step 2. Step 2 is we need to draw the Lewis structures for all of these substances. So we have 3 different substances. We have nitrogen gas, hydrogen gas, and ammonia. And we need to draw the Lewis structure for each one. All right. So you got to dig back into your knowledge of how to draw Lewis structures. Let's go ahead and do that. And we'll start with N2. So for nitrogen, N2, I know I'm going to have 2 nitrogens, and they have to be bonded together at least one time. So I'm going to go ahead and put a single bond there to start. And then we need to find the total number of valence electrons. So each nitrogen has 5 valence electrons, and there are 2 nitrogens, right? 2 nitrogens. So I have a total of 10. So I have a total of 10 valence electrons. There's 2 in that first bond, and I'm going to put the rest as pairs, as we learned. 2, so I go 2, 4, 6, 8, and that nitrogen's full, so I'll move over to the other one and add my last pair. Okay. Now I have all my valence electrons on there. Now I need to see if any of the atoms is not full, meaning it doesn't have 8 valence electrons. This nitrogen here, okay, this nitrogen has 8, so 2 in the bond plus 4, 6, 8, so it's full. But this one here on the left only has 2 in the bond plus 4, so it still needs 4 more, or 2 pairs of electrons. How do we get those? We share them with a neighbor that's full. So I'm going to basically just cross those off and say, all right, I'm going to double bond. Now this nitrogen has 6, and we still need another pair. So I'm going to cross this off, and I'm going to add another bond, so that gives us a triple bond. And now we have the correct Lewis structure for N2, which is nitrogen gas. And I'll just clean this up a little bit. Okay. So now we have a triple bond for that nitrogen, and that's really important when we get to our next step. Okay, let's go ahead. We need to draw Lewis structures for everything. So let's go ahead and draw H2. And actually, I'll clean this up too. All right. So H2, we have 2 hydrogens. So we have hydrogen and hydrogen. We know they're going to be bonded together at least once. How many valence electrons? 1 each. And so that's 2 total. And I already have 2 in this bond. So as I taught you, hydrogen can only have a bond to it, a single bond and no extra electrons. So that's exactly what the Lewis structure for hydrogen looks like, just a single bond between the 2 hydrogens. Okay. All right. And then we just have NH3 ammonia over here. So we'll go ahead and put that in. Now in this case, I'll just let you know nitrogen's going to be our central atom. And then we're going to have hydrogens like this. All right. And we need to check here and see, do we have any double or triple bonds? So let's go ahead and figure out what's the total number of valence electrons. The nitrogen is going to have 5. And each of the 3 hydrogens is going to have 1. So that's a total of 3, which gives us 8 total electrons. Now, just a quick reminder or point. Whenever I'm determining valence electrons and Lewis structures, I'm not paying attention to the coefficients, okay? That's not a factor. When I'm doing the Lewis structure, I'm just trying to figure out what's the structure of one of these ammonias or one of the H2s or one of the N2s. I'm not worried about how many total there are in the balanced reaction. So that's a really important point, okay? All right. Let's continue then. So we have 8 total in this structure that we need to show, and I have 2, 4, 6 total. That means I have a pair left, and the only place they can go is on this nitrogen. So what that really tells us is that in this molecule, we just have a single covalent bond for each of the nitrogen hydrogens. So again, I'll clean this up a little bit. All right. Okay. Now we have all of our Lewis structures. There's a couple of ways we can go about this now. I'm going to show you visually how we would do this. And so instead of, well, I'm going to take into account now the coefficients for each one of these. What the coefficient tells us, like 1 here, it tells us that we only have a 1 of these N2 molecules. So I'm going to leave that one the way it is because I have one there already. But then I come over to H2 and I have 3 of those. So I'm actually going to redraw this Lewis structure, the bonds. Right? That's what we really care about, and this is the bonds. I'm going to draw it 3 times because this coefficient right here is telling me that I have 1, 2, 3 of those molecules, right? And that's going to be really important when we determine the energy to see if it's endo or exothermic, okay? All right, oops, erase that. And then we'll do the same thing over here. And so I'm going to have another one of these in H, H, H. And once you draw the Lewis structure, this extra pair of electrons isn't really important anymore. I'll put them on there, but it's not very important because really what we care about is bonds. We don't really care about extra electrons. And bonds are going to require energy or give off energy. Extra electrons are not significant when we're calculating how much energy is absorbed or released in a reaction. Okay. All right. This is a lot of work already just for one problem. We've balanced the chemical reaction. We've determined the Lewis structures and we've drawn all those out so we see every single bond that's involved in this reaction. Now, the next step is we need to figure out, um, uh, well, in this reaction, all of these bonds here that I'm going to circle, okay, all of these need to be broken in order for these new bonds over here to be formed. And notice that I'm drawing these bonds over here in red because it's going to require energy to break those, and blue on this side, okay, and to show that that's a different type of bond. They're being formed, so energy is given off when those are actually formed. So I guess I should do red on the other side and blue, like switch those, but I'll get to that. So we're going to take a minute and we're going to now go to our bond energy table. Let me go ahead and erase those, okay? And I'm going to look at how much energy does it take. Let's just start. I'm going to switch colors here. How much energy does it take to break a nitrogen to nitrogen triple bond? Now is where our bond energy table comes in, and this is really important. So we come here and we scroll through our list of bonds. Now up here, these are all single bonds on the top. But if we scroll to the bottom, you see, okay, here we've got some triple bonds and we have a triple bond here. And this, that's a double bond. Where's our nitrogen-nitrogen triple bond? That is not, oh, it's up here, sorry. This is our nitrogen-nitrogen triple bond up here. So sometimes you have to look around for them. But the energy for a nitrogen-nitrogen triple bond is 945, and all of these energies are in kilojoules per mole. Don't worry too much about that. Remember, we talked about a mole is 6.02 times 10 to the 23rd of those particular molecules. So we're talking about a lot of the molecules, and we're talking about how many kilojoules or thousands of joules it takes to break that. Don't worry too much about that. You don't need to get overwhelmed with the semantics. So the key is that whether this bond, a nitrogen-nitrogen triple bond, is being broken or being formed, it's always going to be an energy of 945. So I'm going to take that over here, and I'm going to say that energy right there, okay, is 945, and that's kilojoules per mole. I'm not going to worry about writing units down right now. Okay, so I know the energy that it takes to break that bond. Remember, everything over here, we're breaking all these bonds. Okay, we're breaking these. On this side, we're forming bonds. So, but let's focus on one thing at a time. Oops, what's that hydrogen there? All right, now I have the next type of bond that has to be broken is a hydrogen-hydrogen single bond. So let's come to our chart here and let's find a hydrogen-hydrogen single bond. Right here, 435 kilojoules per mole. So I know it's 435. And the thing is, I have three of those, right? I have 1, 2, 3. So I'm going to have to multiply that times 435. And if we do that really quick, 435 times 3, we're going to get 1305. Okay. And if I add that to the 945, so I'm taking this, and I'm adding those together, plus 945. Oops, hold on a second. I've got my calculator off to the side. I apologize. I should have worked these out beforehand, but time has not allowed that. So 2250. 2250. Okay. Now, that is to break all of the bonds of the reactants. It's going to take 2250 kilojoules per mole. Okay, kilojoules per mole of energy. And that's energy that is absorbed. Okay, that's how much energy is absorbed in this reaction. Now, that's only one piece of it. Again, these problems take a little bit of time. You really have to work your way through them. Now we have to figure out on the product side, all of these bonds are formed, right? All of these bonds or new bonds are formed. Bond forming is an energy releasing process. It gives off energy. Over here, this is an energy absorbing process. So we're really comparing how much energy is absorbed, how much energy is released. So now we have to figure out, okay, how much energy is released total. This side's pretty easy because we have all the same kind of bond. We have a nitrogen hydrogen single bond, and we have 6 of them. So we're going to do 6 times, let's see, we got to go figure out how much, whoops, I lost it there. A nitrogen hydrogen single bond. So we're going to search our sheet here. Let's see, where is a nitrogen hydrogen single bond? And I'm not finding it. Here we go over here. Okay. So nitrogen hydrogen single bond is 390. So that's the value that we need to put here. 6 times 390 kilojoules per mole. And we'll punch that into the calculator and we get 2340. 2,340 kilojoules per mole. Now, that's how much energy is released. Okay, so now we can compare these numbers. Overall, we had the bond breaking, which was over here. We broke bonds, and that took 2250. On the other side, we formed new bonds, and that was 2340 kilojoules per mole. So overall, is more energy absorbed or released? And we can see here, this is a larger number. So we know more energy was released in this reaction. Because more energy was released, this is an exothermic reaction. Okay, exothermic. Exo means out, thermic is heat. So because more energy was released when all the bonds were formed, this is an exothermic reaction. Now, one thing that I'm going to ask you to do is determine what is the difference in energy. So if we subtract these two numbers, we just take the 2250, okay, minus 2340. And you can do it, write the bigger number first so you don't get a negative number, whatever. We can just take the absolute value. It doesn't really matter. When we punch that in, I'm not a big fan of this calculator. We get 90. Okay, the net difference is 90 kilojoules per mole. All I did was subtract the difference between energy absorbed and released, and the difference is 90 kilojoules per mole. Okay, so what that tells us, if I asked you, is this an endothermic or exothermic reaction? Okay, you could just tell me this reaction right here, this reaction is an exothermic reaction because more energy is released than is absorbed. This is how much energy is released. And we could also say that what happens to the surroundings in this scenario. And the answer is that the surroundings are going to warm up because it's an exothermic reaction, energy is being released. Okay, so that's one example of how to do this, and we'll look at another one in just a second here. The next problem we're going to go through is this one. So we'll go through this one and we'll finish up. And we have carbon monoxide. You should be able to name these, actually the first two. And chlorine gas, CO2, goes to COCl2. We're missing the yield sign here for some reason. Remember, you need the table of bond energies, so we'll have that. And you're going to need a periodic table because we're going to have to go ahead and write the Lewis structures. So let's go ahead and let me write this out. Carbon monoxide plus chlorine gas, Cl2, goes to COCl2. All right. All right. So remember, the whole goal of this is to figure out if this reaction is endothermic or exothermic. So, on a test, I'll ask you, is this reaction endothermic or exothermic? Prove it. Like, how can you prove it? And all the work we're going through is how you prove it. And then you can also answer the question, do the surroundings of this reaction cool down or do they warm up based on what you figure out? So step one is to balance the reaction. So let's go ahead and do that. Now the nice thing about this one is it's actually already balanced. Like we have 1, 1, 1. So it's not the greatest example for practice, but it still gives you the same idea of what we're doing here. Okay, so we don't have to do any changing of coefficients. The whole reaction is balanced here. Now we need to draw the Lewis structures. So we're going to draw the Lewis structures on both sides. CO, we know we just have C and O, and they're bonded together. Total number of valence electrons is 4 for carbon and 6 for oxygen. That's 10. We have 2 here, 4, 6, 8, and 10. So that's not done though, because this carbon is not full. So we're going to need to share a pair of electrons as a bond here. Okay, now this carbon has 6, and so we need to get to 8. Remember the octet rule. And now we have a good Lewis structure because both carbon and oxygen have 8 valence electrons, and that's 10 total. So that's a good structure. Okay, let's go ahead and do Cl2. So chlorine and chlorine. We have 2 of those, and each one has 7 valence electrons. So we'll do 7 times 2, right? There's 2 there. That's 14. So we have 2 in the bond, 4, 6, 8, 10, 12, 14. All right, so that's full. All the atoms are full. We don't need to do any double bonding, and that's really important because single and double and triple bonds have different values, and so it's important to know that this is just one single bond. Okay, I'm going to draw my dividing line between reactants and products. Let's go ahead and draw this big molecule, which you shouldn't know how to name because it's more than 2 different atoms, and so we can't use prefixes and stuff on this. It has a common name. We won't get into that because you don't really need to know it. So let's go ahead and draw this. Which one's a central atom? Carbon is a central atom because it has only 4 valence electrons and it wants to share 4 times. Oxygen, on the other hand, has 6, so it only has 2 places to share. Chlorine has 7. It only has one place to share. Carbon is our central atom. Let's go ahead and bond all an oxygen and 2 chlorines to that, right? Okay, and now we need to count up our valence electrons. Carbon has 4, oxygen has 6, that's 10. Each chlorine has 7, that's 14. So 10 plus 14 is 24. In the bonds, we already have 2 there, 4 there, 6 there, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, now do a quick check. Do any of the atoms not have 8 valence electrons? And if you said carbon, you are correct. It only has 6, right? 2, 4, 6. So we need to share a pair. Now we have this question, well, who do we share with? A chlorine or an oxygen? If you remember, chlorine's Lewis structure looks like this, and it only wants to share one time here. But oxygen looks like this, and it wants to share 2 times. So it's more likely that we should share a pair from oxygen and double bond there than the chlorines. That's something you should know by now by practicing the Lewis structures, right? Okay, so now we have a good Lewis structure. Let me clean stuff up a little bit. We have a good Lewis structure for COCl2. We know where all the bonds are, and that's going to be really important as we figure out the bond energies. So that's our next step. Let's figure out how much energy is on each of these bonds. Remember on this side, okay, this is all bond breaking. So we have to break this bond and we have to break this bond, only 2. Let's go to our bond energy table. We're looking for a carbon oxygen triple bond. Let's see what we got here. So where's our carbon oxygen triple bond? Okay, right here. Okay, 1070 carbon oxygen triple bond, 1070 kilojoules per mole. And then we need to look for our chlorine chlorine single bond. Chlorine chlorine single bond is going to be, where are you? Oh, here it is. Right here, 240. Okay, so 240, we only have one of those. Remember, if our coefficients weren't 1 up here, we would have to account for more than one of each of these molecules. But they're only 1, so we're going to, we have one of each, so we only have to count the bonds in each one of those. All right. If we add that up, 1070 and 240, what does that give us? 3, 13, 10, if I'm doing my mental math right, which sometimes I mess up. 40 and 70, yes, I think that's right. All right. This is how much energy is absorbed from the surrounding environment to break the bonds over here. Remember, this is breaking bonds. Okay, that's important. That's an endothermic or energy absorbing process. Excellent. Now let's go to the other side, and we have a couple of kinds of bonds here. We have a carbon chlorine single bond, and we have 2 of those. So we need to go figure that out. How much is a chlorine carbon single bond? So let's look for that. We have carbon, we have chlorine right here, 330 kilojoules per mole. Chlorine carbon single bond. Okay. I just forgot what it was. Chlorine carbon 330. Okay, there we go. 330, 2 times 3, 30 is of course going to be 660. Then, so we got those. Now we have this carbon oxygen double bond, and we just have one of those carbon oxygen double bond. I think we saw that recently. So a carbon oxygen double bond, again up here, is 1070. Okay, so we have 1070. And I did that format a little differently. We're just going to add all of those up. Okay, so we got 1070 plus our 660, and we get 1730 kilojoules per mole. Now, that is released. Right, so the next question is, after we break all the bonds over here, Oops, that was supposed to be blue. That's important. Okay. After we break all the bonds here, and then we form all the bonds here, is more energy absorbed or released in this reaction. And we can see overall, more energy is released. To figure out exactly how much, we can go ahead and subtract those numbers. 1730 minus 1310. And what do we get? Minus 1310 is 420. 420 kilojoules per mole is released. Okay. So overall, this is an exothermic reaction. Exothermic. How do I know it's exothermic? Thermic. I don't know why I added the X there. X. So we know this is exothermic because more energy is released, making this an exothermic reaction. When we form bonds, that's an energy releasing process, and more energy was released when we formed the bonds than was absorbed when we broke the bonds over here. So overall, this is an exothermic reaction. And if I asked you what happens to the surrounding environment, does it cool off or does it heat up? In an exothermic reaction, energy is given off to the surroundings, so everything around it is going to heat up. Okay, excellent. Go through one more example just to give you a little more practice here. This is kind of one of my favorite reactions. This is called, well, it's really the decomposition of water, and we can do that through electrolysis. So remember, a decomposition reaction starts usually with one reactant, right? Decomposition, and it forms smaller, like simpler substances. So in this case, we form H2 plus O2, right? Turn my notifications off. All right, so again, we want to know in the electrolysis or the decomposition of water, is this an endo or exothermic process? Does it give off energy overall or does it absorb energy overall? That's the process here we want to look for. Okay, again, first step, balance the reaction. So let's go ahead and go through the formal process. We have H's and O's in this whole reaction. On this side, if we start with ones for all of them, because we have to start somewhere, we have 2 and 1. Over here, we have 2 and 2. So to balance this, we're going to need to go ahead. Maybe we'll start with a 2 over here, because that'll balance our oxygens, right? But it also gives us 4 hydrogens and 2 oxygens. So the oxygens are balanced now, but the hydrogens are not. So we need to come here now and put a 2 there. And that gives us 4 hydrogens. Okay, so that's going to balance our reaction 2-2-1 for this. If I got that right, let's clean it up to go to the next step. And yeah, I'll just go ahead and do 2, 2. Okay, 2-2-1. Ah, that's down to 11. There we go. Okay, so we got our balanced reaction. Guys, you can see why it's so important that you can balance the reaction here, right? That's a critical piece to all of this. And it is in a lot of chemistry. Balancing chemical reactions is kind of a fundamental concept in chemistry, kind of like multiplication tables in math. You know, it's just so important. All right, so we got our balanced reaction. Next step, let's go ahead and get our Lewis structures down. So we have 2 H2O molecules. Remember, I'm going to ignore the 2 when I'm drawing the Lewis structure. All I care about is this, H2O. It's in the circle here. So we've already drawn the Lewis structure for water multiple times by now. Oxygen's in the middle, hydrogen's bonded there. Total number of valence electrons we have is 6 for the oxygen and 2 for 1 for each hydrogen for 2. So that's 8 total, and I already have 2, 4, so we need 2 more pairs. 6, 8. All right, we got our Lewis structure there. Remember, I have 2 of those, so just for the sake of a visual, like the visual people, right? Let's go ahead and draw it again so that we have 2 water molecules. And remember, they're not connected to each other. They're not bonded together. We're just saying that the ratio here is 2 water molecules overall for all of this, okay? Sorry about that. Okay, let's go ahead and keep going. So the next thing is we need to draw the Lewis structure for H2. We did that just a bit ago. We saw that it's just H and H like this, right? Pretty straightforward. And that's all we need to do there. And we have 2 of those, 2. So let's do that one more time. And then we need to go ahead and draw our 1 oxygen molecule. So oxygen is going to be bonded at least once. Let's go through the process to draw the Lewis structure. Make sure we get it right. You can't assume how many bonds there are. That's a good way to get yourself in trouble. So we've got 1, 2 there. How many valence electrons does each oxygen have? 6. And there's 2 of those. So 2 times 6 is 12. Good grief, I'm getting blown up. Sorry, guys, for all the distractions here. So we have 2 here, and 4, 6, 8, 10, 12. We see this oxygen here is not full. It only has 6. So we're going to share a pair from a neighbor to fill it up, right? And so we get that double bond here, and I'll clean that up for us. Oh, goodness. All right, clean that up. So we have a double bond in that oxygen molecule. And again, that's really important because a single oxygen bond has a lot different energy than a double oxygen bond or a triple bond between something. That's really critical for all of this. Okay. All right, now we've got our Lewis structures drawn. So driving me a little crazy. I'm going to clean this all up a little bit. Okay. So again, for visual, we have 2 of these water molecules, right? We have 2 of these hydrogen molecules, and we have 1 oxygen molecule. So we drew the Lewis structures and we drew out each one. Now you might have noticed, you don't need to redraw these. Like it's kind of excessive to redraw them. All you really need to do is find out for one of them what's the energy and then multiply it by 2. So if you've seen that already, that's great. That's a shortcut. It's really a way to save you time, but sometimes it's easier again for the visual people to kind of see that instead of just to think it through mathematically. Um, okay, let's go ahead. The next step. We need to figure out how much energy is associated with all of these bonds here. So let's go ahead and look at our endothermic side, which is this side over here is bond breaking, which is an endothermic or energy absorbing process. And we have 1, 2, 3, 4 of those oxygen, hydrogen, single bonds. Oxygen, hydrogen, single bonds. So let's go to our table and find oxygen, hydrogen, single bond. I seem to not be finding it. You guys probably already found it. Here it is. Oxygen, hydrogen, single bond. I think we already saw that one somewhere else. Is 460. Okay. Oxygen, hydrogen, single bond, 460. So 4 times 460. And again, we'll just punch that into the calculator, right? 4 times 460. And it's going to give us 1840. Now, those are the only bonds that we have to break here, those 4 bonds for this reaction to happen. And that is energy absorbed. So we're done with that side. Now, on the product side, all of these bonds are formed with the new products, and that's an energy releasing process. So we need to figure out how much energy is released overall when all of those bonds are formed, right? So let's start with 2 of those hydrogen single bonds. Let's find that again. Hydrogen single bond here, 435. Okay, great. So 2 times 435 is 870. Okay. And then we have 1 oxygen double bond. Oxygen double bond. And that's going to be up here. Now, I failed to mention this already, but I'm going to tell you now. You can't just come to the oxygen single bond, wherever that is on here. Right here, look at oxygen single bond is 145. If you're like, well, I've got 2 of those, so I'll just double it. It doesn't add up, right? An oxygen single bond is 145. If you multiply that times 2, you get 290. If you have an oxygen oxygen double bond, it's actually 495. That's a big difference. So you can't do that. You have to find the specific bond energy for each of these, and we can't get into why that is. That's a AP Chem level stuff. Why a bond, a double an oxygen oxygen double bond is much higher energy than an oxygen oxygen single bond. eh, we're not going to get into that, but it's true, and you need to just know for our class that you can't just double or triple numbers. You have to find that energy for that specific bond. That's critical. Okay. All right, now I just lost what I was talking about. So 495 is the energy. Do we write that down? 495 here. So we need to add those. We need to add those together, right? The 870 plus the 495, and we're going to get a total of 1365, and that is released when those bonds are formed. Okay. So again, now just like all the other ones, right? We need to see more energy is absorbed in this reaction than is released. More energy is absorbed. That makes this reaction an endothermic reaction. Okay. By how much? What's the difference here? So let's subtract them. 1840 minus 1365. And when we punch those numbers in, 1840, we're going to get 475. And again, this is all kilojoules per mole just for the sake of the video. It's already long enough. I don't need to keep adding units and stuff. It's the same for all of these. So that's the net energy change that 475 kilojoules per mole is absorbed in this endothermic reaction. And so then again, if I ask you, well, does that mean that the area around this reaction is going to cool down, or is it going to warm up? And because it's endothermic, energy is going to be absorbed by this reaction from the surroundings, causing the surroundings to cool down. All right, energy is being taken, thermal energy is being taken from the surroundings, and that's going to cool everything off. So this is an endothermic reaction, cooling things off. And like I said, this process is kind of cool. In order to break water apart, you can actually do this. You can take a 9-volt battery and put it in some water. You add a little bit of salt to it, okay? Because you have to have an electrolyte in that water to conduct the electrical current from the battery, and you'll actually start to see bubbles that'll form. And those are usually oxygen and hydrogen bubbles that are forming. And you're basically running an electrical current, you're taking electrical energy, and that is breaking those bonds. It's supplying enough energy to break all the bonds apart and form the new products, which is kind of a fun little process. That's one of the ways that we can create hydrogen gas, right? This hydrogen gas right here is a great fuel source. We can put it in cars, we can put it in rockets, we can combine it with oxygen and reverse this reaction, which gives off a lot of energy as a combustion reaction, and power things by hydrogen power, which is a very clean and efficient energy source. It just takes a lot of energy to make the hydrogen. So we got to figure out ways to make the hydrogen without having to use a lot of other energy. Okay, you guys are tired of listening to me. I've talked a lot. I've shown you a lot of examples. I hope that that helps you understand how to determine if a reaction is endo or exothermic and actually what that means, right? Good luck and Scourge.